Okay. Um, my name is Alex Altair, and the rest of the teammates are listed below here on this slide. This is the presentation for the project that is described as does sufficient optimization imply agent structure? That's what we call the agent structure problem, which is posed by John Wentworth. And that's what we spent the project working on. But mostly for this presentation, I'm going to talk about what we mean by structure, or what we sort of hope to mean by structure, and why I think it matters for AI safety. So we all have some beliefs about how AI systems are potentially very dangerous. But these beliefs are, I think they're like valid and correct beliefs for the most part, but they're based on, they're not based on experience directly, like in the same way that like we experience malaria as dangerous. We haven't like seen a bunch of AGIs happen. And they're not based on like formal methods of understanding things. So like super volcanoes might be dangerous, for example, but that's sort of because we like understand the physics involved and we like know where they might be. Instead, the arguments about AI risk are really trying to predict something that might happen. And they're sort of what I would call philosophical or conceptual arguments. And I think this makes it quite hard for us to know exactly what to do about it. And it also makes it harder to convince other people that it's that much of a risk. So I think there's an overall issue where we need to really refine these intuitions in what I would hope would be a mathematical sense. Okay, so what are some of the things that we think make AIs dangerous? Well, there's capabilities, which is something people talk about all the time. More capabilities means more dangerous. What goes into capabilities? Well, there's compute power. There's training on more data. If the AI systems sort of like know more about the world, if you give them all the data about the world, then they can have a bigger effect. And then the more interaction they have with the world, like if it's sort of an autonomous AI, then it has a higher ability to, has higher capabilities. But that's a danger, but it's sort of not, it's like necessary, but not sufficient for it to be dangerous because like there's data centers all over the world right now that are, churning through a bunch of compute power and a bunch of data, but they're just like serving images or something like that. And we can sort of just tell, well, those aren't the dangerous ones. So there's something particular about AI that makes it dangerous that isn't just capabilities. A couple other analogies that I like to use are this claim about capabilities is really a thing with any tool. Like if you have a really big hammer, you can hit bigger rocks. You can break open bigger rocks with it, but you can also like hurt yourself more, or you could like hurt someone else more with a bigger hammer. And another analogy is with energy, like physical energy. Energy is sort of by definition the thing that lets you make a bunch of changes in the world. Like the more energy you have, the more changes you can make. And most changes are bad, so energy is dangerous. But somehow humanity has like organized society with like these enormous energy channeling infrastructures, and it's like not that bad. It's like a little dangerous, but it's not going to like burn down the whole world, right? We sort of like understand mechanistically how it works enough. So there's something else about AI that's a little bit special. When you read literature about AI risk, people will use various phrases to sort of like gesture at this thing or this cluster of things. They might say that the AI systems are dangerous if they're like goal-directed. So if inside the AI's mind somehow it has a goal that it's like going for and it's like trying to achieve the goal, or if it's like a utility maximizer and it's trying to like try really hard to like maximize utility, that's somehow more dangerous. Because coupled with capabilities, it might like select some action that we didn't think of that had like big side effects or whatever. Another term or another thing people talk about is how can you tell when an AI system or machine learning system is just a bunch of heuristics? One of the talks yesterday talked about, can we tell if a system is doing search on the inside? General purpose search seems to be like more dangerous than just a bunch of heuristics somehow. So these are all talking around something that is about the internal structure of the machine learning system or the AI system, as opposed to the capabilities, which is the behavior. So we can observe capabilities, But that's just sort of, we make a machine learning system, we run it a bunch of benchmarks, and we say, wow, it could do all those things. It seems like it could do other things that are equally large or equally impactful, but the internal structure is what determines what the system actually does. So it's an example of a structure, somewhat more specifically, somewhat more algorithmically. An ideal agent is this concept that you can formalize if you wish. So an ideal agent will do something like it'll have prior beliefs over all possible worlds, and then it will observe. It'll receive observations through its sensors, and then it will do like ideal Bayesian updating about those observations, and then it will consider every possible action. Calculate the implications in every possible world, calculate the expected utility of each action, and then take the action that has maximum expected utility. This is an algorithm. It's well defined, like mathematically, if you wish. There's some details, obviously, to fill out. But it's also not something that's going to actually be implemented in a machine learning system because it's totally impractical. But I think that there's going to be lots of approximations to this kind of structure, to this kind of algorithm. And I think it stands to reason that many approximately ideal agents will have approximately optimal performance. So there's this sort of like cluster around approximately ideal or approximate agent structure. And we want to understand how to locate that kind of distance. We want like a distance measure between structures or something like that. And the agent structure problem specifically actually asks the inverse of this statement at the bottom. The agent structure problem is asking, if we merely observe behavior that is nearly optimal, then can we infer that the structure of the thing doing the optimization is approximately an agent? And naively, the answer is no, but you need to like figure out a bunch of conditions, a bunch of like criteria that make this true, or you can ask like which ones will make it true, and after we find those, is that do we think that's a compelling match to like what a machine learning system is, for example? So one idea that comes up pretty quickly when you consider this question is, okay, well, maybe if all we observe is the behavior of the system and we observe that it acts optimally, well, it could be, in theory, that inside the system, there's just a table that just, whatever the observations are, it like looks them up in a row of the table, and then the returned value is just happens to be the ideal action. And it has a row for every possible observation in all the environments. So this is like mathematically possible, like it exists as a function, but it's obviously not an agent. And so in some sense, it's not the dangerous thing. But it's also not the thing that would actually be implemented in a machine learning system because it's impractical also. It's basically exponentially large in like the number of time steps. So a thing that you need to do in the theorem that you want to state and prove about agent structure is you need to say, okay, well, it has near optimal behavior, and it's like not that long of a thing to describe. So whatever your like policy class is that you've defined in your theorem, it will need to have some sense of like description length of the different structures, and we can say, well, okay, we don't want it to be a table, and we don't want it to be like a thing with a bunch of pre-computed caches. So we'll say it has a limited description length. Another consideration is the environment class that you observe optimal behavior in has to be pretty diverse and rich to imply agent behavior. So mazes are a very popular environment class for AI for a variety of reasons. If you saw an algorithm optimize in all mazes, you would be impressed, but you wouldn't be like, oh no, it's an agent. Not necessarily. It seems like you can have non-agents that optimize in the environment class of mazes. So the environment class has to be pretty diverse. And then to leave you with like a teaser of some potential math or whatever, there's this big looming question of like, what the heck is structure and how do we tell that something is approximately structured like an agent? And the current idea that like we're excited about and that like my team is sort of all learning about is algorithmic information theory, aka Kolmogorov complexity as a field. I suspect that they have techniques where you could answer this question, where you could say that one particular algorithm is epsilon bits away from some other algorithm. So we're hoping to make progress using that tool. Okay, I'm all done.